All right, so here's what we're going to do tonight. We're going to do this thing called probability, and I was just giving a little example of probability. Probability involves randomness, and if you do, the example I gave was if you flip a coin, and it's a perfectly even heads and tails coin, and you flip it, everybody said the probability of getting a head is 1/2, or 0.5. Probability of getting a tail is also 0.5 or 1/2. If you roll a 6-sided die, from dice, right? If you roll a 6-sided die, the probability of getting a 2 is 1 out of 6. Probability of getting a 3 is also 1 out of 6. So we'll talk about those sorts of things when we do that. So here's the first thing you need to know about probabilities. Okay, a probability is always, and by the way, when I say this always, it's always true, and some of you guys will not make your probabilities meet the following case and you'll get them wrong, even though this is always true. Probability is always between 0 and 1. Okay, so if your probability comes out as 22, it's wrong. Can't be. It's got to be between 0 and 1. Inclusive. It can be either 0 or 1, but it can also be anywhere in between. Okay? Or we can say that it's 0% probability or 100% probability. Okay? And remember, percent means multiply by 100 for whatever or divide by 100 to get the actual value. So it's still a number between 0 and 1. Okay? When we talk about probabilities, we have to talk about experiments. An experiment, okay? An experiment is any occurrence for which the outcome is uncertain. Is any occurrence for which the outcome, I think my handwriting is getting worse as the year goes on, for which the outcome is uncertain. In other words, you don't know what's going to happen when you do something. Could be lots of different possibilities. Okay? We say that the set of all possible outcomes is called the sample space. The set of all possible outcomes is the sample space. Okay? So there's basically three vocabulary terms here, right? Probability, which we know is always between 0 and 1. An experiment is any occurrence where you don't know the outcome. And finally, all the outcomes taken together is called the sample space. Okay? So for instance, let me erase the top one here. For instance, the sample space for the heads and tails, for the coin, we just say that the sample space equals, we put these curly brackets here, and we say h comma t. That's the sample space. Isn't that all the outcomes you can get from flipping a coin? Therefore, the sample space is just h comma t. Okay? And an event is the subset of the sample space. So you can say the event, this is the other one, I guess, an event is what did I say it was? A subset of the sample space. A subset of the sample space. Sample space. So for instance, in this case, the event might be heads, right? The event might be it came up heads, something like that. Okay? For a coin. Coin comes up heads. Okay? All right, a couple more theoretical things here we have to talk about. Okay? An experiment of the following type. If we have an experiment, okay, we call it n. In other words, the number of the sample space, that many equally likely outcomes. Okay? The outcomes are done this way, n of e. Don't worry about all these, by the way. Okay? That's the number of outcomes. Okay? We say that the probability of event e, we actually say the theoretical probability. We're just going to call it the probability. The probability of event e is the number of events that are possible, or sorry, the number of outcomes divided by the number in the sample space. Right? So I'll show you what this means with an example. So what's the theoretical probability of getting heads when flipping a coin? Well, we already know it's 1/2, right? If the theoretical probability of getting heads, so how many different ways can the coin come up? How many different ways if you're flipping a coin can it come up? Just 2. So the number of outcomes, okay? Sorry, the number of outcomes, okay, is 2, and the number of likely outcomes in this case, you're only going to flip it once, equals 1. So we do 1 divided by 2, and that's the probability. Okay? Or you could think of it this way. The sample space is, as we said, heads and tails. And the likely event is going to be, let's say, heads. And therefore, it's 1 in this one and 2 in this one, 1/2. Okay? Again, this is just the theoretical stuff. All right? Let's look at doing a die, like I mentioned before. Okay? If you have a die, you're going to get the sample space for a die is what? What can come up when you're rolling a die? Yeah, but the sample space is actually 1, 2, 3, 4, 5, 6. That's actually the sample space, right? You're right. The number of outcomes, the number of the samples is 6. The number of the sample space is 6. Okay. Let's say that you want the probability of rolling a 1 or a 2. You can either get a 1 or a 2 on this die roll. You're playing some game and you want a 1 or a 2, right? Well, what's the probability of that? This is just 2 there. So we just do 2 divided by 6, or 1/3. All right? And if you think about it, these are the choices, right? Well, how often are those 2 going to come up? There's 3 different parts. There's this part, and this part, or 1 out of the total of 3 different parts. Okay? You can think of it a couple different ways if you want. Okay? How about same thing, a die, and let's say that you want to roll a number less than 10. What's the probability? What's the probability of rolling a number less than 10 out of a dice? 1, 2, 3, 4, 5, 6. You can roll any of those, right? So the number of likely outcomes is also 6. 6 divided by 6 is just 1. You're always going to get a number less than 10 if you roll 1 die. It's just the way it goes. Okay? All right. Let's see. What if you want to roll an even number? What's the likely outcomes going to be? 2, 4, and 6. And so NE is going to be, how many are there? 3. And so what's the probability? 3 divided by 6, or 1/2. Yeah, question?
That's on the homework?
This stuff's on the homework, yeah.
That we're doing now, that's for tomorrow?
No.
Sure?
Pretty sure. Should be on next week's homework.
I've seen some.
Uh-oh. Maybe you're doing the wrong homework. Uh-oh. Hope not. All right. So last week I said we're going to do some things with cards, like decks of cards. Okay? And we have to do probabilities are really good with cards because there's lots of different ways to deal cards and lots of different games you can play. And if you're going to be a gambler, right, you want to know something about probability, or you won't be a very good gambler. Because if you didn't know basically what your odds or what the probability of getting a certain hand is when you have such and such cards in your hand, you're not going to do very well if you're gambling. Some people just gamble it for fun, which is great. But if you gamble to like try to win, well, you better know something about probability. OK, so let's say you're dealt a 2-card hand. We're going to play a 2-card hand from a 52-card deck, our normal deck, 52-card deck. Okay? What's the probability of getting a pair of 2s? Probability for a pair of 2s. Okay, probably getting a pair of 2s. Let's see how we might do this. We have to do a little bit of counting for this to figure some of this stuff out. Okay? Pair of 2s. All right, well, first of all, let's look at the sample space here. To get 2 cards, okay, this is kind of going back to last week for a minute. Okay? The combinations. Okay? If you're trying to get 2 cards, okay, well, how many choices do you have for the first card? 52 choices for the first card. Okay? And how many choices for the second card? 51 choices for the second card. Right? Does it matter what order they're in? So you actually have to divide this by 2. Okay? Because of that. But let's do it the way we looked at it last week and say the following. Really, this is saying 52 cards chosen 2 at a time, or 52 cards combination 2. Okay, remember this from last week? It's like dredging up some stuff from last week. Okay, what we're saying is 52 cards taken 2 at a time. And if you look on your formula sheet, right, what this works out to be is 52 factorial. Remember, 52 times 51 times 50 times 49 times 48 all the way. Okay, divided by 52 minus 2 factorial. And because the order actually doesn't matter, you're going to also do times 2 factorial because it's a combination. Okay? Okay. So what this actually means is this is going to be 52 times 51 times 50 times 49 dot 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 all the way down to 1. This one is going to be, let's see, 50 times 49 times 48 times 47 dot 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 times 2 times 1. Okay, that's the extra term there. There's an extra 2 times 1 there. So guess what? All the 50 to 49 goes down, and all you're left with is 52 times 51 divided by 2. If you do that out, it turns out that there's 1,326 different ways to take 2 cards from a deck in your hand. It's 1,326 different ways. Okay?
Just 2 cards.
Just 2 cards, because you're only choosing 2. Remember, we're just getting a 2-card hand. Okay? If you want to pick 2 cards, there's 1,326 different ways to do that. Okay? Now, let's look at the number of outcomes there are.
Chris, is that 52 minus 2 or is that 52 times 2?
52 minus 2. Look on your formula sheet. You'll see it right there. Now, on your calculator, you probably should learn how to do this on your calculator. The 52 choose 2, and then it should give you 1326 real easily.
What is it again?
On the blue calculators, I think it's the PRB button, maybe. Is that one of them?
Okay.
And you have to choose you have to do like, what you would do is 52, and then that PRB, and then choose the little C, or NCR, I think it is, and then hit 2, and then hit equals, should get 1326. Okay. All right. Now, we're looking for a pair of 2s. Okay? How many different 2s are there in a deck of 52 cards? There's 4 of them, right? And how many are we choosing? 2. So the number of likely outcomes, we can only do 4 cards choose 2 cards. Okay? That is the same exact formula here. It's going to be 4 factorial divided by 4 minus 2 factorial times 2 factorial, which is 4 times 3 times 2 times 1 divided by, this is going to be 2 factorial, 2 times 1 times 2 times 1. That 2 times 1 goes away, and that one does. And you're left with 12 divided by 2, which is 6. So there's only 6 different ways to get a pair of 2s. Okay? In all these 1,326. So what's the probability? The probability of getting a pair of 2s is going to be the number of likely outcomes divided by the number in the sample space. 6 divided by 1,326. Okay? Which, if you reduced it, it'd be 1 over 221. Is that number between 0 and 1? Sure it is. Right? Do it on your calculator. 1 divided by 221. Okay? It's probably a pretty small number. Who needs a calculator? Who needs to borrow a calculator tonight? 1. Anybody else? There you go. All right. So what is 1 divided by 222? 0.0045 blah blah blah. Right? 0.0045. So is it likely that you're going to get a pair of 2s if I just dealt you 2 cards from a deck? Not very likely. 1 out of every 221 times I did that, on average, you'd get a pair of 2s. So not so likely. What's that? It's not pocket aces. Yeah, it's like.
Everybody else comes up.
That's the same thing. Pocket aces are exactly the same thing, right? Yeah. About every 221 hands, somebody gets a pocket ace. And if you're playing, what is that? Texas Hold'em? Is that what it is? Yeah. Yeah. You know. So when they show you that on like ESPN3 or something like that, they don't show you every hand a lot of times. They show you like a lot of hands, but not every hand. What's that? OK, so that's a fairly simple one. Let's look at another one. Another one that is involving cards. Okay, let's say you get a 5-card hand. Okay, so same thing, 5, except now it's 5 cards, like a regular old poker hand. 5-card hand. Okay. From a 52-card deck, we can say 52-card deck. Okay, 5-card hand from a 52-card deck. What is the probability of getting a full house? I'll tell you what a full house is, for those of you who don't know. Okay? Or somebody can tell me. Full house? 3 of a kind and 2 of a kind. Okay? So it's basically you're getting 3 of one card, 3 of a kind, and 2 of a kind, or a pair. We'll just call it a pair, which is 2 of a kind. Okay? So we have to do a little bit more thinking for this one. Okay? All right. The number of outcomes here is going to be the following. This one takes a little bit of thinking to figure this one out. Okay? For the 3 of a kind, okay, you're trying to choose from how many different cards to make that 3 of a kind from. How many different numbers are there out of a deck? 13 for every suit, right? Well, yeah, there's 13 each suit, so there's only 13 different choices for the 3 of a kind. You can get a 2 or 3 or 4 or a jack or a king or all the ones in between, right? And an ace. Okay, so there's 13 different ones, right? So what we're going to do is we're going to say 13, and it's not going to be a choose thing, because there's 13 different ways of doing this. Okay, but how many cards are you choosing? Well, just for the 3 of a kind, you're choosing 3 cards. Okay, and each number has how many total in it? 4. So you're actually doing 4 choose 3. So this is just for the 3 of a kind part. Okay? There's 13 different cards in each, that you can choose from, 13 different numbers, including the face cards. Okay? Times the way you can make a 3 of a kind from each number. 13 times 4 choose 3. Okay? So that's for the 3 of a kind. Let's use the same argument for the pair. How many different cards are there now once you've got your 3 of a kind in terms of for each like number? So, well, let me rephrase that. So I go and I deal Terrence 3 cards straight off the bat, right? And those cards are a 4, 4, and a 4. Can he also get a pair of 4s? No. Once he's got the 4, 4, and 4, how many different numbers left are there to choose from? 12 different ones left. 12 different ones left. Now, the same argument as before. How many are we choosing for the pair? 2 out of how many cards in a number? Like how many of each number are there in the deck? 4. So isn't going to be 4, choose 2. And the reason I added is because we're just counting up the numbers of choices here. Okay, this was a tricky one. And I wouldn't have expected you to necessarily to get this one straight off the bat. But do you get the argument now? We're saying first there's 13 cards we can choose from, 13 numbers we can choose from. And then of those 13 numbers, we've got to choose 3 of them out of the 4 for each one that's available. And then for the pair, there's only 12 left because we've already got the 13 for the full house, or for the 3 of a kind. There's 12 choices left. And now you're picking, of each 4 cards in those choices, you're picking 2. Okay? When you do this out, okay, this actually equals 3,744 different ways to do this. Okay? Why are you laughing? That's not what you got? 13 times 4 choose 3 plus 12 times 4 choose 2. You can do that on your calculator, but you can. On your calculator? Yeah. Well, there's 2 different ways to do it. You can do it the long way, or the writing it out way, or you can use your calculator. If you use your calculator, I'll do it on one of the blue calculators, this one. If you do it on this calculator, what you would type in this one is 13 times 4. Then you'd hit the PRB button, and you go over and you'd choose NCR because we're doing combinations. And then you'd hit 3. Now I think you should be able to just hit plus right now. 12 times 4, and then the same thing, PRB, NCR, 2, and you get 124. So you can't do that. So what you have to do is you have to do it in parentheses. So you have to do the parentheses before you do this. Let's try that. Does it? Yeah. Did I do it wrong? I might have done it wrong. Hang on. Let's see.
Because 13 or 4 choose 3 comes out to be 52.
Right, I got the same answer.
OK, times 12. 12 times 4 choose. 4 choose. Oh, you know what? Maybe you have to do the whole thing for parentheses. Let's try this. 13 times, in parentheses, 4 choose 3. 52, OK. Plus, did I say plus? You know what? It's not plus. I lied to you. It's times. Because you're multiplying all these together. I bet that works out better.
Circle of trust.
I know, circle of trust. Yep. Is it 3744 now? Yeah. OK. Times 12 times 4 choose 2. 3744. Did it work that time?
Yes.
Yeah, OK, sorry. OK, so why did we have to multiply? Well, because you're first doing this, then you're doing this, and they're both happening for the same deck of cards, basically. So that's why it's going to be multiplied. Question? Aaron? No. Looked like you had your hand up. OK. So 1,344. Now, what's the number of sample space in this case? How many cards are we choosing now? For a full house, you've got to have how many cards? 5 of them. right? Out of the 52 card deck, 52 choose 5. Well, I bet that number's not too big. 2,598,960 different ways to deal 5 cards out of a hand, out of a deck.
You're being facetious.
OK? I was not being facetious. All right. It is pretty big. So now 3744 divided by 2,598,960 equals 0.00144, or 0.14%. Not 14%, but 0.14%. Right? Which is really pretty small. You are not going to get dealt a full house very often. And think about it. If you've ever played cards, you don't get full houses very often, right? Where you get 3 of one kind and 2 of another kind. It's pretty rare. Well, it's rare because only, one time out of, let's see, that would be 1 out of 10, 1 out of 100, 1 out of 1,000 times you might get a full house if you're dealt 5 cards. OK? Kind of crazy, huh? All right. This, I'll leave that right there. OK. There's another way. This was the theoretical probability. In other words, we're thinking about this, and we're just kind of, we're using the numbers based on these counting things. If you have a different situation where you observe a certain number of events happening, and you know how many times you did the events total, like let's say you flip a coin 10 times. Right? Anybody have a coin or a pog?
There's a coin right here.
Look at that. There's a coin right here. OK. I'm going to flip this 10 times. And we're going to write down. Actually, somebody else is. Who wants to? You can flip it. Mike?
Flip the coin?
Go ahead. Flip the coin and just write down. Tell me what you get. You're going to do it 10 times.
Heads.
Heads.
Tails.
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 Heads.
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 Tails.
Tails. Didn't we already do that? Yeah, 1, 2, 3, 4, 5, 6, heads, 7. 3 more.
Tails.
Tails.
That's the second time this one's gonna play.
I know.
Heads.
Heads and 1 more.
Heads.
Heads. OK. So Mike did this, and he said, all right, heads, tails, tails, heads, heads, tails, heads, tails, heads, heads. And we did it 10 times. OK? What's the probability of heads in this case? We're calling this empirically. Empirically means we did an experiment, and we're going to use the experiment to give us the probability. OK? In this case, the probability of heads is, well, we know it's out of 10 times. So how many heads do we get? 1, 2, 3, 4, 5, 6. 6 out of 10, or 0.6. So the empirical probability of getting heads in this case is 0.6, just from that little experiment. Now, would we trust that experiment?
No.
Not really. Why? Well, it does change, but let's think about why we trust any experiment. Most of the time, is 10 experimental values enough to tell you what's going to happen? I mean, couldn't you have, if you had done things right, just done 1 head and all the rest tails? And then we would have said the probability is 1 out of 10, right? So the theoretical probability can differ from the empirical probability because you've done the experiment. But if I said, Mike, go home and flip that coin 10,000 times, the odds are we'd get a number pretty close to 0.5. Maybe not exactly. It might be 0.493 or something like that. But that's pretty close to 0.5. OK? You willing to do that? Yeah. All right. Actually, I had a professor in college. I was taking a probability class, and he was talking about this exact sort of thing. And he said, tonight, I want you to either do one of the following things. Go home and either flip a coin 100 times and write down all the answers, and just write them down in a line on your paper. or just make up the answers. Just do 100 H's and T's and make them up yourself. And he said, I guarantee you that I'll be able to tell you who really flipped the coin and who didn't. And we all went, oh, yeah, whatever. And so the next day, I think I went home and I didn't do either. I think I wrote a little computer program to make it happen, but because I'm nerdy. But anyway, so the next day he said, OK, get out your homework. And we all got our homework. And he went across and he said, you actually flipped it. You actually flipped it. You didn't flip it. You actually flipped it. You didn't. You didn't. You didn't. Got everyone right. Whoa. And we're like, whoa, that's pretty cool. Well, it turns out that when you're flipping a real coin and you do it 100 times, the odds are, the probability is very good that you will get at least, I think it's 6 either heads or tails in a row. Just because of the way it works out when you're flipping coins that many times, the probability is very, very good that you will get that. Now, how many people wrote down a run of 6 in a row? No, nobody did when they made it up. They didn't know that. They didn't know that there probably should be a run of somewhere in there. So that's when the guy went around. Yeah. So go ahead and prove it. No, don't prove it. But it's another kind of That's a different like kind of level of probability. But the point is that you can do an experiment and then get an empirical probability by doing that experiment. Okay. All right. Any questions on that? All right. So that's the beginning part of probability. Okay. Now we've got to look at, actually, we're skipping section 11.5. I forget exactly what it's about, but we're not going to do it. So there shouldn't be any problems from 11.5 on the homework. I don't think there are. We're going to go to 11.6, which is, we're calling this events including not, N-O-T, not like K-N-O-T, like in your shoe, not and or. So we're going to say things like, what is the probability that you do not get a 6 or something like that? Okay. And then we'll talk about probabilities like what happens if you roll a 2 or a 5, something like that. Okay. So let's go to, and we're also going to talk about these things called odds, which is what you do when you're like betting on horses and things, or betting on basketball tournaments, so that sort of thing. They always talk about the odds, right? We'll talk about what that means. It's actually very, very closely related to probability. Okay, so it's not that hard. So let's say you roll another die. Okay, so we roll a die. Okay, roll a die. Let's just say that we're going to define uppercase E to mean we're going to roll a 1. Okay. What do you think not E would be? Yeah, how about roll a 2, 3, 4, 5, or 6? Does it make sense? If you have something, E is roll a 1, not E is roll anything else other than a 1. Why doesn't it include 0? You can't roll a 0, right? Or it doesn't include 7. It's only in what the choices are. So we're talking about a die which has 1, 2, 3, 4, 5, 6. If E is roll a 1, if the event is roll a 1, not E, or not the event is roll a 2, 3, 4, 5, or 6. Okay? What's cool about this idea is if you have the probability of some event, that equals 1 minus the probability of not that event. Okay? This is actually kind of neat. Let's see if this works. For our case up here, okay, we roll a 1. Okay, what's the probability of rolling a 1 on a die? 1 out of 6. Okay? What's the probability of rolling not a 1? 5 out of 6, because there's that, right? 5 out of 6. What is 1 minus 5 out of 6? 6 out of 6 minus 5 out of 6 is 1 out of 6. Okay? So sometimes it's easier to do, if you say, what's the probability of something, it's actually easier to calculate what's not the probability of doing that. And if you can do that, subtract it from 1, and you will get the probability of the other choice. Okay, I'll show you an example of that here. Okay, another a choice where it's actually easier to do the opposite case. Okay, so let's say you're dealt one card from a deck. One card from a deck, from a 52 card deck. A 52 card deck. Okay, so you got one card. Find the probability that you are not dealt a heart. Probability of not a heart. Okay, probability of not a heart. Well, let's say that the event is you are dealt a heart. Okay. How many different ways are there to get dealt a heart? 13, right? Number of events, 13. Number of likely outcomes is 13. The sample space is going to be 52 cards, right? So you've got 52 cards. Okay? So the probability of a heart is 13 out of 52. Right? But the probability of not a heart is 1 minus 13 out of 52. Right? So that's actually 52 minus 52 divided by 13, or minus 52 divided by 52, which is 1, minus 13 out of 52, right? Which is 39 out of 52. Okay. And 39 out of 52 happens to be 3/4 equals 3/4. Okay. 1 out of 52 happens to be 1/4. So 1 minus 1/4 is 3/4. Okay. That's not too bad. All right. So let me show you another example where it's actually a lot easier to do the exact opposite. In your book, on page 637, you don't need to look there, but on page 637, there is a chart. What's that?
Not past S. Not past S.
Not past S. OK. All right. I will draw this. This is going to take me a couple seconds to draw here. OK. This is a pie chart, okay? And it looks like the following. OK, let me see if I can do this pretty quickly. Oops, that should be in the middle. That was not in the middle. I know, I already screwed up. OK, so let's see. Here's the middle. Yeah, you know what? That one's not going to happen. It's way too loud. If you want to somebody wants to turn these other ones up, we can. Yeah. Aaron, you want to just stand up and see if you can crank that one up more? Might already be up as much as it goes. Yeah, it is, isn't it? Is it? And it's on? Yeah, sorry. Robert, you can move down in here. Maybe you get a little arrow down here. Sorry about that. During the break, you can turn it on and cool it down. OK, so let's see. So I'm going to make a pie piece like this, and then another one. These should be different colors, but I don't have time really to do different colors. And then like this, and then this, and then this, and then a tiny one there, and another tiny one there, and another tiny one there. OK, so it's like a pie piece. OK, and what we're going to say, this is the number of car drivers by age group. Number of car drivers by age group. OK, lots of different age groups here. So if you're less than 19, less than or equal to 19, there's actually 9 million of you. OK, if you're less than or equal to 19. 20 to 29, there's actually 33 million. 33 million. OK? 30 to 39, there's 40 million. 30 to 39, there's 40 million. OK? 40 to 49, there's 40 million. 40 million. OK? As well, so same amount, about 50 to 59, there's 31 million. 50 to 59, 31 million. From 60 to 69, there's 19 million. 60 to 69, there's 19 million. Okay, and 70 to 79, there's 13 million. 70 to 79, there's 13 million. And actually, let's see, there's only one more category. I put too many categories. Greater than or equal to 80, there's actually 6 million drivers. Okay, so I'm going to, I know. Let's pretend, and they're all in Arizona. Okay, let's just do this. 80, greater than or equal to 80, there's actually 6 million. Let's pretend that was small. Now, pretend these are all different colors. Okay. What is the probability that a randomly chosen driver is not in the 50 to 59-year-old age group? So this is the 50 to 59. Okay. If you were to do this by saying, well, if they're not in the 50 to 59, then you got to do this one, plus 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 this one, right? OK. Well, you kind of have to add them all up to begin with. But you can actually do this. It says in here there are 191 million total. OK, so you don't even have to add it up. 191 million drivers total. OK? The probability of not being in the 50 to 59 group, OK, not 50 to 59, that's our we want the probability of that. Probability of not 50 to 59. Well, it's just 1 minus the probability of being in the 50 to 59 range. OK, I'll put it in quotes there. Right? So how do we do that? 1 minus the probability of 50 to 59. Well, there's 31 million divided by 191 million. Do 1 minus that, and you'll get your answer. So it's pretty simple to do, right? That makes sense? And in this case, it's going to be 1 minus 31 over 191, which actually equals 160 divided by 191, which is, let's see, not on my other page, so we have to actually do this out, which is what? 0.84. 0.84. And it should be between 0 and 1, which it is. Okay? And it means about 84% of drivers are not 50 to 59. That's what this means. Okay? Which just makes sense because most of the rest of this pie is not drivers 50 to 59. Okay? Kind of a long example to just do that, but that's that. OK, let's do this. Let's take our break now, our first break now. OK, because I can see some things, and it's getting hot in here, so you can crank that up now if you want. Good. How did I do it? 160 divided by 191? Yeah. All right, let's get going. So I wrote a bunch of things down here, so I'll give you time to write this down. But the next thing we're going to talk about is this idea of or. If two events happen, if one happens or another event happens. The first thing we need to talk about is if you've got two events, but they can't occur at the same time, what we say is we say that those events are mutually exclusive. Okay, it's another vocab word if you want. Mutually exclusive. In other words, they both can't happen at the same time. One happens or the other happens, but you're not going to get both. Okay? If that's the case, what we say is the probability of A or B is just the probability of A plus the probability of B. Earlier I screwed up and said plus when I meant multiply, but now we really are doing plus. If you can do one thing or the other, they can't happen together, you can do the probability of the one plus the probability of the other, and you end up with the total probability. Okay? All right, and here's the example. I'll let you guys finish writing the top part down. Okay? Mutually exclusive. Except for you people who came in late. Mutually exclusive. Okay, it's just going to be addition. Okay? All right. Here's the example. Let's say you pick a card from a 52-card deck, and I say, what's the probability of drawing a face card or a 2? Face cards are what? Ace, king, queen, or jack. Okay? Ace, king, queen, or jack. Okay? Ace is considered a face card. Yeah. Okay. So how many different face cards are there? 16. So I guess ace might not be a face card in this case, because I have 12 written down. Let's see. 4 times 3 would be 12. You're right. It doesn't matter. Well, I said it already. We'll say we count ace as a face card. Aces don't have faces, though, do they?
No, they don't. That's why.
All right, all right. All right, well, we won't count them. I'm wrong. We won't count them. OK, so the probability of, so there's how many face cards are, if we're not counting aces, there's 3 per suit times 4 suits. So there's 3 times 4 equals 12 face cards. OK. All right. How many 2s are there? 4. Face cards, 2s. There are 4 total 2s. Can you get a face card that's also a 2? No. So choosing a 2 or choosing a face card are mutually exclusive events, because you can't get a 2 that's also a face card. OK? So this is actually pretty easy. The probability of a 2 or a, should be an OR, or a face card, OK, equals the probability of getting a face card, or probability of getting a 2, which is 4 out of 52, plus the probability of getting a face card, which is 12 out of 52, 12 out of 52, which equals, I'll put what I like to do right here, 16 out of 52. See how easy that is? They're mutually exclusive. You can just say probability of one plus the probability of the other. 16 out of 52, which is actually 4 out of 13. 4 out of 13. OK? All right. Sometimes, though, cards are not, like, events are not mutually exclusive. OK? I'll erase the blue, not the yellow. OK? All right. Still writing down yellow. I'll make the next one blue. If A and B are not mutually exclusive, if A and B are not mutually exclusive, we have a different way of calculating the probability. The probability of A or B equals the probability of A plus the probability of B, so far the same, minus the probability of A and B. Okay? Let's think about what this would be. How would I change this example so that those two cards would be not mutually exclusive? Ah, there we go. Let's say, what is the probability of choosing a face card or a heart? Good example. A face card or a heart. Can you get a face card that's also a heart? Yes, so those are not mutually exclusive. OK? All right, and let's see. I actually used the example of a heart or a 2. Let's use that example. OK? The probability, so you draw a card. So the example now is draw a card. And what is the probability? What is the probability, okay, of drawing a heart or a 2? Drawing a heart or a 2. Okay. Can I erase the yellow? All right. OK. How many hearts are there? There's 13 hearts in the deck, because there's ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king of hearts. So there's 13 of those. OK. How many 2s are there? We already said that. 4 2s. OK. And how many 2s are also a heart? 1. OK. 1, 2 of hearts. Okay. So the probability of a heart or a 2 equals the probability of a heart plus the probability of a 2 minus the probability of the 2 of hearts, which in this case is probability of a heart, 13 out of 52. The probability of a 2, 4 out of 52. Subtract away the probability of 2 of hearts, 1 out of 52. 13 plus 4 minus 1 is 16 out of 52, or 4/13. Okay, I'll let you write that down. Tuan's giving me this look like I'm crazy. Let me explain what's going on here. Okay? I do want you to write it out. If you're writing things down, I want you to write it down so you can then pay attention to what's going on here. Why do you think we have to subtract out the extra part here? Because actually, yeah, you're both right. Go ahead, what did you say? Yeah, you're doubling up on the extra part that's not exclusive. And you're kind of double counting in some sense. When you count all the hearts and you count all the 2s, you've double counted that 2 of hearts. Right? You counted it here and you counted it here. So you actually have to subtract out that extra 2 of hearts in the probability. And that's why you do this subtraction. So it's not too bad when you think of it like that. I'm trying to see if a lot of this stuff is on your formula sheet, by the way. Down here it says probability of not E is 1 minus the probability of E. It says the probability of A or B is the probability of A plus probability of B. And then it also says the probability of A or B equals the probability of A plus probability of B minus the probability of A and B, exactly what we have here. It doesn't say that it's for mutually exclusive. You've got to know that. But it is, the formulas themselves are on here. Okay? Yeah. Makes sense, Sharifa? The A and B part? 2 of hearts is A and is the heart and 2. Okay. All right. Any questions on this stuff? Can I erase it?
You gotta go back.
I gotta go what? We're good?
I just need numbers up there.
You need numbers?
Yeah,
There's numbers right here.
yeah, 30 words before it.
Uh-oh. Well, it's on the video, and it's all on the notes that I post online now too, right? So yeah. Okay. Now we're going to talk about something that's kind of fun. We're going to talk about odds. Okay. As in, if you're horse racing or betting on horses. Okay. Here's how odds work. Okay. P of E is the probability of an event. Is the probability, just like we've been talking about all night, probability of an event. Okay. The odds, we have two things. One, if P of E is the probability of an event, we have the following. One, the odds in favor of E are found by the following. Okay, it's actually pretty easy. Odds in favor of E are found by the probability of E divided by the probability of not E. Okay. We also have, and sometimes you'll hear this, the odds against. The odds against E. Okay. are found, found by, okay, the probability of not E divided by the probability of E. It's exactly flipped. Okay? Didn't we say that the probability of E equals 1 minus the probability of not E? Okay. Turns out if you add this to this, you get the total number of events. Okay? You get the number of the sample space. You get the total number of samples. Okay? As it turns out. Okay? This becomes very handy when we're trying to figure out if we've got odds in the right format. Let me give you an example. Okay? Here's the example. This is where people, all this like, formulas and things up here sometimes doesn't make sense to people. But once you do it, you'll see it's really not that bad. Okay? All right. Draw one card from a 52-card deck. We're going to find the odds in favor and the odds against drawing a heart and then drawing a queen. So we're going to find the odds in favor of drawing a heart. Let me leave this stuff up here, and then let me just put this kind of on the side. Okay? All right. So what is the probability of finding a heart? What's the probability of getting a heart? 13 out of 52. So this is for a heart. OK. So for this one, 13 out of 52. What's the probability of not getting a heart? 52 minus 13, 39 out of 52. Right? OK? This actually equals, the 52s actually cancel out. And the 39 actually ends up, sorry, the 13 over the 30, it ends up being 13 over 39. Okay. The odds against a heart down here is exactly the opposite. It's just going to be, instead of 13 39ths, it's going to be 39 13ths. Okay. We'll do another example in a little bit once we get to slightly easier numbers, you'll see where this will start to make a little more sense. Okay. All right. How about a queen? The odds in favor of getting a queen.
Just any queen?
Just any queen. So how many queens are there in the deck? 4. So the odds in favor are 4 50-seconds divided by how many? What's the probability of not getting a queen?
48.
What's that? 48 out of 52. 48 out of 52, which is just 4 out of 48. Okay? And in this case, you can actually do this. That's actually what is that? 1/12? Yeah. 1/12. Okay? What's that? All right. The odds against getting a queen are going to be 48 out of 4, which is 12 to 1. The odds against getting a, what did we say? This one was a queen, right? The odds against getting a queen are 12 to 1. That's how we say this, by the way. We say 12 to 1 against. Okay. Let's do a slightly different example. Let's say before I do the different example, let me show you how to convert from odds to probability, because once you do this, you'll go, that makes it easier. And you'll always be able to figure this out. I'm just going to erase it all right now. Sorry, if you need it, I can put it up later. OK. To go from odds to probability, OK? So let's say that the odds, let's say we're talking horse racing, OK? And the odds of winning the odds in favor of a horse winning a race. So the odds in favor of I don't know, what's the name for a horse?
Windbreaker. Seabiscuit.
Seabiscuit. The odds in favor of Seabiscuit. That's the name of that's in the movie, right?
Yeah.
Seabiscuit, right? The odds in favor of Seabiscuit winning, and I have no idea if this is good or not for Seabiscuit because he normally won races, are 5 to 8. Okay? And let's actually write it like this. You'll see it a couple different ways. You'll see it maybe like this, 5 to 8. You'll also see it like this, 5:8. Okay? So the odds in favor of Seabiscuit winning are 5 to 8, like this. Okay? What's the probability of the horse winning? What is the probability? Okay, of the horse winning, I should say. Probability of Seabiscuit winning. Okay, we know, right, that the sample space is this number plus this number. When we did it like this, we said that the one on the bottom plus the one on the top is the total amount of the samples. Okay, so in this case, it's going to be 5 plus 8, or 13. Okay? Well, the nice thing is the probability of winning is just 5 out of 13. You take the first number and you divide by the total of the two. Okay? How would we go backwards? It's actually pretty easy. To go backwards to the odds, you'd say 13 minus 5 is 8, and you do 5 to 8, or 5 to 8. Now, let's think about it this way. Let's think about it slightly differently. If you have a coin like we did before, flipping a coin, okay? What's the probability of a head? 1/2, right? OK. So the I'll do it right over here. OK. Coin. OK. The probability of a head is 1/2. What are the odds in favor of getting a head? 2 minus 1 is 1. 1 to 1 odds. Now, think about what that means when you think about what odds means. If you have 1 to 1 odds, that's a 50-50 chance, basically. Okay? So that's how I like to think of it this way. I like to think, if I have a probability of 1/2, that's 1 to 1 odds. Okay? Let's go the other way. Let's say we had 2 to 1 in favor of something. Okay? 2 to 1 in favor of something. All right? Well, how did we go to the probability? For the probability, we said 2 plus 1 is 3, and we take the first one over there, 2/3. So is 2 to 1 in favor a good probability, or good odds? 2 to 1 in favor is really good odds. If you see a horse, like maybe Seabiscuit was like 100 to 1 odds, right? Do you want to make a bet on that horse? Yeah, you really do. Because the probability is going to be 100 divided by 101, which is actually really pretty good. What's 100 divided by 101? 0.99. That means that basically 99 times out of 100, Seabiscuit wins. Okay? Okay? Yeah. It's got wheels, right? Now, if you're the other way, let's say you are 100 to 1 against. Well, you do the exact same thing. You add the two together, but you put the other one up on top, right? So if Seabiscuit broke a leg, then Seabiscuit would be like 101 against winning, right? And you would be 100. You'd be 1 divided by 101, which is a really small amount. Okay? Yeah. And you would normally, well, yeah, you could write it 100 to 1 against, and that would mean the odds against winning. Okay? So let's see. Let's do another one. Let's say we had 3 to 4 in favor of winning? Winning. That's the odds. Is that a good bet? Would it be a good bet to bet on that or not? I don't know. Let's see. It's going to be 3 plus 4 is 7. 3/7. What's 3 divided by 7? 0.43, or 43% chance. So it's a little less than even. If you're a 3 to 4 in favor of winning, it's a little less than even. So a lot of times you'll see the horses that are winning are more likely to win the race. You'll see a bigger number on this side because the odds are normally in favor of winning. So you'll see like 7 to 6 odds. Well, that's not too bad. That's 7 out of 13 probability, right? Which is greater than 50% when they do it that way. Okay. All right. Any question on odds? You'll do some of those on homeworks too. Okay. But I always remember if I forget everything about odds, I just say, all right, what are the odds of getting? What's the odds in favor of getting a coin flip to be heads? 1-to-1 odds, because it's 50-50 chance is 1-to-1. That means 50-50 chance, or well, that's not the. I think that's still an odds, by the way, 50-50 chance, right? 1-to-1 odds. And how do you figure that out? You add them together, 2, and you do 1 divided by 2 is the probability. Okay? That's how I always just remember how to convert back and forth. Okay? All right. Okay. That's odds. All right. Good. Section 11.7. So last time we used or, and we used not. This time we're going to use and. Now we kind of used and a little bit before, but we'll do it a little bit. So this is 11.7. Okay? This is events involving and also and conditional probability. Conditional probability is kind of cool. Conditional probability means when you know something that's already occurred, you can change that changes how you calculate some other probability. Okay, it's kind of cool. Okay. Before we were talking about mutually exclusive events. Okay. We've got another concept which is slightly different. Actually, it's very different, in fact. Okay? We say that two events are independent if the occurrence, I had to look how to spell occurrence, occurrence of, I hope I did it right, if the occurrence of either event has no effect on the other. Or I should say on the probability of the other. On the probability of the other. Okay? Events involving and. Two events are independent if the occurrence of either has no effect on the probability of the other. If you have independent events, the probability of A and B equals the probability of A times the probability of B. And this one now is a times. Okay? All right. Is the yellow hard to read back there? Sorry. I'll stop using it. I like it. It looks nice up here. OK. Let me do an example. I'm not going to erase I'll erase this part. OK. Here's what we mean. Or here's an example. Draw a card from a 52-card deck. Draw a card. And it's going to be a 52-card deck again. OK. Return it. Then return the card. Okay. And then draw again. Okay. What is the probability of drawing a heart twice? Probability of drawing a heart twice. Okay. Are these independent events? Drawing the heart once, does that affect drawing the card the second time? That's a key point here. Some people might think it does. Like, if you pick a heart the first time and then you put it back in the deck and then you try to pick another card, some people think, well, because I picked the heart the last time, this time it's going to be a different probability. It's not. The deck is exactly the same. Let's say you reshuffle, right? The deck is exactly the same, like, randomness involved. Okay? The two probabilities here, or the two events here, are draw a heart and draw another heart. Okay? So here's what it is. You've got event A is draw a heart. Draw a heart. And event B is also draw a heart. Okay? Well, what's the probability of drawing a heart? 13 out of 52, right? Or 1 out of 4, because there's 4 suits, and you're either going to pick hearts, clubs, spades, or diamonds. 1 out of 4 for the probability of A, right? And the probability of B, probability of B is also 1, 4. Oops, I did it wrong. I'm writing it wrong. Sorry. Probability of, I know you have to erase. Probability of A, I'll do it this way. A and B equals 1/4 for the probability of A to draw a heart times 1/4 for B to draw a heart, which is 1 out of 16. Okay? Yeah. Let's do another one. What's the probability of let's see. What's the probability of choosing the 6 of spades? Like I take a deck and I grab one card. What's the probability of being the 6 of spades? 1 out of 52. What's the probability of shuffling it back in and choosing the same card again? 1 out of 52. But to do it twice in a row, it's 1 out of 52 times 52, right? Which is really poor odds. Yeah. Yeah. Okay. So point what?
2704.
1 out of 2704. Yeah. 1 out of 2704. Okay. Here's another independent events thing. Okay. Anybody have 2 siblings? 2 siblings, but not more than 2, just exactly 2? You the middle? Youngest, you the middle? Oldest? Middle? Old, oh, no middles, huh? No Jans, the family? What is the probability? What is the probability of a family having 3 sons in a row? Anybody, you guys, 3 sons?
I think it's more.
No? 3 daughters?
Two brothers.
You have 2 brothers? Yeah. It's pretty unlikely. Okay. To have 3 sons in a row. Okay. What's the probability of having 1 son? 1/2. Right? Is that an independent event from having another son? Aside from like maybe some men only produce sons or whatever. Let's say it was random, right? Yeah.
Why is it not 1 out of 3?
Just we're talking either son or daughter.
Oh, yeah.
First one, son or daughter, right? Okay. Yeah, unless there's some other choice that I don't know about. But okay, so son or daughter, 1/2. That's the first son. That's son number 1. Son number 1. Son number 2, 1/2. Son number 3, also 1/2. 2 times 2 times 2, 1 out of 8. Right? 2 times 2 is 4. 4 times 2 is 8. Okay. My mom happens to be in a family of 7 daughters, no sons, right? What's the probability of that happening? 1/2 times 1/2 times 1/2, 1/2, 1/2, 1/2, and one more. 7 daughters, right? 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. 32 times 2? 64. 64 times 2? 128. 1 out of 128 times, if you have 7 kids, you're going to end up with 7 daughters or 7 sons, right? So yeah, that was, they kept. Unfortunately, my grandfather had no brothers and sisters, and so his name was gone now. Like there's no and he had no cousins or anything, right?
He kept trying though.
He kept trying, yeah. One of my cousins actually did end up taking his last name, which is kind of cool. So she ended up taking his last name. So it still exists. But anyway, OK. So that's how you do these probabilities when they're independent events. OK? Different from mutual exclusivity, because mutually exclusive means the same event can have 2 different parts that are overlapping in some sense. This is not an overlapping one. This is like one event, then another event. OK? All right. Actually, I guess I can erase this too. OK. The next thing is the probability of an event happening at least once. The probability of an event happening at least once. Yeah, like being struck by lightning. Equals, OK, 1 minus the probability that the event does not happen. Now, there's a key here, at least once. So you could get struck by lightning 20 times, right? That's at least once, right? It's 20 times, right? But the probability of something happening at least once is 1 minus the probability that the event does not happen at all. Okay. Let's do an example. All right. Anybody from Florida? Where?
Orlando.
Orlando. There you go. Ever been in a hurricane? Probably been in like 5. No? How long did you live there for?
4 years.
4 years.
Jacksonville, yes.
Jacksonville, yeah. So here's a question. If the probability that a hurricane hits South Florida in any given year is 5/19, so the probability of a hurricane hitting South Florida, okay, in a given year, is 5 out of 19. Okay? All right. Question A. What is the probability that it's hit in 4 consecutive years? Probability 4 hurricanes in consecutive years. Okay? That's the question. This one we just did, basically. Okay? What's the probability that it's hit in the first year? 5/19. What's the probability it's hit in the second year? 5/19. The third year? 5/19. In the fourth year? 5/19. So this is the probability that it's hit in 4 consecutive years. Okay? That is 625 divided by 130,321, which equals, or it's approximately equal to, 0.0048. So it's not very likely that you're going to get a hurricane 4 years in a row. Dwan?
Where did the 519 come from?
I made it up. Or it might be some statistic, I don't know. But let's say we made it. Let's say it's a statistic that the Weather Service gives you. Good question. OK. All right. Let me erase the top thing here. We're going to use this in a minute, though. OK. All right. Sometimes I'm writing too big. OK. Question B. What's the probability that it's not hit in the next 4 years. Probability of not hit in the next 4 years. Okay. You would think it'd be 1 minus, but it's not in this case. Okay? Because that was saying it got hit. This one was saying it got hit in 4 consecutive years. This one's saying it's not hit at all in the next 4 years. Okay? All right. But we're going to ask another question there. But in this case, OK, in the first year, what's the odds that it's not hit? That's where you're going with this one. 19 minus 5 is 14. So in the first year, 14/19 not hit. The second year, 14/19. The third year, 14/19. And the fourth year, 14/19. In this case, that's actually 0.295. Okay? So that's actually not too bad. I mean, 30% chance, basically, that it's not hit in the next 4 years. Here's the last question. What's the probability that it's hit at least once in 4 years? Probability of at least once in the next 4 years. Now, see how that's slightly different than both of these questions? It's saying it's not that it's not hit in the next 4 years, that it's hit at least once in the next 4 years. This is where you can use that probability, OK? It's actually the probability of being hit. Right? We said earlier, what did we say? We said the probability of it happening at least once is 1 minus the probability that it does not happen. Isn't this the probability that it does not happen? Not hit in the next 4 years. So it's the probability of hit at least once is equal to 1 minus 0.295, which is about 0.705, right? Or 70.5% chance. So let's look at what the differences are here. Probability that you get hit every year in the next 4 years, very, very, very small. The probability that you don't get hit at all in the next 4 years, medium. Probability that you get hit at least once, pretty big. See how that works? Because
He proved it wrong. He was there for 4 years.
and you were there for 4 years and you didn't get hit. Well, he didn't prove it wrong. He just happened to be in the 30% that didn't get hit in that 4 years, right? Yeah. OK. All right. A couple more things here. So we said we had independent events. OK? We can also have dependent events. OK? Dependent events are exactly what you might think. OK? Two events are dependent if one of them affects the other. OK? Dependent events. Dependent events. The occurrence of one event has an effect on the probability of the other. OK? All right. Here's how you figure out this, if you know that there's a dependence here. The probability of A and B equals, again, it's the probability of A times the probability of B. Whoops, almost probability of B given that A occurred. OK. Let's step back and see if we can figure out what that means. Probability of A and B. Probability of A times the probability of B given that A did occur. OK? Here's the example. draw a card, but don't replace the card. Okay? Draw a card, or I should say it this way. Draw two cards without replacement. Okay, so you take the deck, you grab a card, you look at it, you put it aside, then you grab that second card. Okay? Does the first card affect the second card? Sure it does, right? Because it could be, if you're trying to find some card and you pick one out, well, first of all, there's less cards left. So that's one thing. And second of all, that card, what you actually picked is a certain card. And it can affect the other ones. Okay? So let's see. Event A. Event A. First card's a heart. This is like the other one before. First card is a heart. Event B. Second card's a heart. Second card is a heart. Okay? All right. Well, the probability of getting a heart, we already know that. 1/4. Right? Times the probability of getting a heart given that you've already chosen a heart. How many hearts are left if you've already chosen a heart? 12 left, right? So this is going to be 1/4 times 12 out of 51, because there's not 52 cards left. I could have written this one. This may make more sense. 13 out of 52 times 12 out of 51. We actually did something like that, I think, right at the beginning, right? Where you said, first you choose a heart. Well, I guess we didn't, but we've done something similar. The first choice, there's 13 out of 52 cards. The second time, you've already gotten rid of one of the hearts. So therefore, it's 12 out of 51 remaining. Okay? And in this case, it happens to be 1 out of 17 chances, probability. Okay? All right. We call the probability of an event occurring if the other event has occurred conditional probability. Okay, let me write that down. This is conditional probability. Okay? Conditional probability. Like that. Okay? This is the probability that event A has occurred. Sorry, that event B, the probability of event B given that A has occurred. Probability of B given that A occurred. Okay, which is what we just used. Okay? We actually say it this way. Probability of B given A. It's just a big vertical line, just like that. Okay? All right, let's do an example of this, another example of this. All right. OK. You select a letter from the alphabet. Aaron, give me a letter. What is it? B. OK. So you select a letter from the alphabet. Find the probability of, well, actually, OK, that is a consonant. We're going to find the probability of selecting a consonant given that the letter is before J. So you actually picked B. That's good. That is a consonant before J. Okay? So we want to find the probability that the letter is a consonant, okay, given that it is before J. Okay. Here's how we'd write that, like this. We'd write it probability of a consonant given precedes J. Okay. All right, let's see what it's going to be. The sample space here. All the letters that precede J, A, B, C, D, E, F, G, H, I. No J. Okay? Sample space is 9. A through I is there's 9 letters there. Okay? And how many consonants? 1, 2, 3, 4, 5, 6. Okay? There you go. So the number of consonants NTS is 6, and therefore the probability is just 6 out of 9, or 2/3. Okay? That's actually not that hard. You just basically, if you do one of these problems where you have, given that something's occurred, get rid of everything else that hasn't occurred and use that as your sample space. That's how easy that is. Okay? Let's do one more card example. Okay? I'll do it right up here. Let's do it right up here. One more card example. Okay? Card is drawn from a 52 card deck. What's the probability that the card is the 2 of hearts given that it is a heart? Probability of the 2 of hearts. How's that? Probability of the 2 of hearts given that it is a heart. There we go. Probability of the 2 hearts given that it's a heart. Well, how many hearts are there? Number of hearts, 13. And the number of 2 of hearts? 2 of hearts, just 1. So the probability, 1/13. Probability is 1/13. So that's not too bad. If you know that, just get rid of what you can't do. We will do some problems. In fact, I think you do have some on your homework that involves this stuff. I forget if it's coming up or it's not coming up. We're going to have to do some examples of this where you have a chart and it lists a whole bunch of probabilities, and then you have to use those probabilities given some questions like this. Okay, so we'll do some examples. In fact, I'll try to find some examples in. I don't know if there's any here. Yes, there are. There's actually exactly one. We'll do it after we take a break. Come back at 8, and we'll do some of these. All right. So this is the kind of problem I was talking about. Okay, this is the kind of thing that you will definitely see on the final. So learn how to do this stuff. Okay. Here's the question: a class is collecting data on eye color and gender. They organize the data collected into the table. Numbers in the table represent the numbers of students from the class that belong to each category. So how many males have brown eyes? 22. How many females have green eyes? 12. Make sense? OK? All right. So here's the 4 questions we have to do. OK. Find the probability that a randomly selected student does not have brown eyes. OK? So you look and you go, OK, the probability of not having something, the probability is probably 1 minus, whoops, I should do it this way. The probability equals 1 minus the probability of not having brown eyes. In other words, the probability of having brown eyes. That's one way to do it. OK, you could say that. So what's the probability of having brown eyes? Well, let's see. The probability that a randomly selected student does not have brown eyes. OK, how many total students are there? Are there? Did you already add that up?
Yes.
How many total students?
Oh, wait.
No.
Two male and female. There's 100.
Is there 100? Let's do this. I always like to do it this way. I always add up the rows and then add up all the columns. Then you can add things a little bit easier. So let's go. How many brown-eyed people are there? 0, 1, 40? OK. And how many blue-eyed? 38. And how many green-eyed? 22. OK. So the total here should be what? 40 plus 38 plus 22? 100. OK. All right. Let's look this way. Let's go this way. 22 brown eyes, 18 blue eyes, and 10 green eyes for the males. 22 plus 18 is 40. Plus 10? 50. OK. And how many females? 20 plus 18 is 38, plus 12 is also 50. Did it add up to 100 that way too? OK, so it did. But now you've got a lot more stuff on there. OK, so does not have brown eyes. Well, how many have brown eyes? The probability of brown eyes is what? 40 out of 100. So the probability of not brown eyes equals 1 minus 40 out of 100, or 60 out of 100. Or you could have just said, fine, the probability of not having brown eyes, 38 plus 22 is 60 out of 100. Either way, you could do it either way. Okay? Probability of not having brown eyes, well, these people don't have brown eyes and these people don't have brown eyes. Did it matter which are male and female for this question? Not at all. OK. B. OK, the probability of a randomly selected student has brown eyes or blue eyes. This is actually kind of an easy one from this standpoint. OK? Any student, how many students have brown eyes or blue eyes? Brown eyes and blue eyes? 78 out of 100. Done. OK, that was pretty easy. Or you could have used our OR rule, which means you add them together, because they are actually mutually exclusive. You can say, or I should say, independent. Yeah, you could say 20, or you could say 40 plus 38 out of 40 out of 100 plus 38 out of 100, 78 out of 100. Same thing. Okay. All right. Next one. What's the probability that randomly selected students is female or has green eyes? Okay. Female is what? Yeah, 50 out of 100. So female, the probability is 50 out of 100. Okay. How about green eyes? Green eyes is 10 out of 100. But did we double count? Is it 10 out of 100? Hang on. Sorry, I'm not really reading it. Hold on. Green eyes. Look, green eyes. The probability of any student having green eyes is 22 out of 100. Right? OK? So if we added those two together, wouldn't we double count? Yes. Right? OK, we would double count some of the green eyes who are female students. So you subtract how many? The green-eyed female students, which are 12 out of 100. OK? So 50, so that's 22 minus 12 is 10. So 60 out of 100? Okay. Probability is 60 out of 100. Can we do it a different way? Female or green eyes? There's really no, there's not another easy way to do that one. That's the way you should probably do that one. Probability of female or green eyes. OK, now this last one. What's the probability that the student is male given that the student has blue eyes? This is actually pretty easy when you see it in chart form. You can't do it the same way you did the last one. Because what it actually is, I think, easier. Because first of all, given the student has blue eyes, do we care about the brown-eyed or the green-eyed students at all?
No, get rid of them.
They don't. You just get rid of them. Brown eyes or green eyes, you're done. So you're only looking at the males that have blue eyes. So how many males have blue eyes? 18 out of how many blue-eyed students? 38. See how easy that is? 13 out of 38. Okay. A lot of you will look at this and go, I don't get it. Not a lot. Some of you will. Don't do that. Practice this problem and really get an understanding of what it means to have female, let's say, female or green eyes. Want to make one up that we can figure out? Let's make one up. Whoops, I erased the numbers. What's that? It's going to be a lot like this, yeah. Like this question. OK, what's the probability that that a female student has blue eyes? (20 out of female student 50, right? That's one of those ones where it's actually So I said a female student has blue, did I say blue? Yeah, blue eyes. This is actually saying the probability that a student has blue eyes given that the student is female. Isn't that what it means?
Isn't that kind of what D is saying too?
That is, actually. That's exactly the same. I just said it backwards. I said the probability that a female student has blue eyes is the same as saying, oops, it's the same as saying a female student. It'll click on in a sec, I hope. Oop, maybe not. There we go. I've said if the probability that a female student has blue eyes is the same as saying, what's the probability that a student has blue eyes given that the student is female? It's just reversing it.
Then would you say that it was 1838? Wouldn't it be 1850?
Yeah, for male, but we're doing female. Right? Yeah. Didn't we do it that way last time? We did it that way last time. No? What do-
We did, the last one was, would be like the same way we say would be is female given the
Oh, you're right. It's the other way around. Yeah, you're right. It's not or, though.
No, for D.
For D. Is male given the student has blue eyes. So you look at the given the student has blue eyes. That's this column.
What do you say is male?
Right, male. Right. I'm saying female. 20 out of 50. I just rewrote it with female
Yeah,
instead of
but
male.
I mean, the last one that we did, that one should have been 18 out of 50, right?
Yes. Which it was, I think, when we did it, no?
No, because it was 18 out of 38. Because
Oh, it is 18 out.
saying,
Yeah.
let's take all blue-eyed
Right.
people,
18 out of 38.
so that one of those blue-eyed
Right.
people being
See,
male.
that's what
Whereas what we're saying now is let's take all the females, and what are the chances that one of those females has blue eyes?
Right, so it's not exactly the same as this one. It's the, yeah. So female has blue eyes. Yeah. Now we're saying, look at all the females. How many females are there? 50, 20 out of 50. We did it this way.
It looked the same way.
Well, they don't. Look, well, this one is male given the student has blue eyes. That's how many total students have blue eyes. 38, right? So what's the probability that the student is male given that the student has blue eyes? So I misspoke. This is not the same reverse. This is not all the same as that. This is a different problem. This is saying what's the probability that the female, it is a female, right? And it has blue eyes. The other one is saying if the student has blue eyes, what's the probability that the person is male? Not the probability of having blue eyes. So it's that's why it's different numbers. So I did misspeak before. OK. All right. Any questions? We're going to do more practices on these. Yeah, Ben?
On these questions, like when we answer, is the things we just write like percentage? Like,
I want a probability.
so it has to be a fraction?
You should, well, if you said, yeah, some people might say, 41. Well, that doesn't tell me anything.
I'm looking like
If you said 41, well, 41% is not a probability. Probability is between 0 and 1. So I guess, all right, fine. If you put 41%, that's fine. I would probably accept that, yeah. But just just answer it correctly, and I'd be even happier. Like 0.41 or whatever, right? OK. All right. Any questions on this one? OK. Let's do this. Let's go over the practice quiz for tomorrow, OK? Which I think I have here. Here it is. And I will do it like this. OK. All right. Let's just go over the whole thing. If you have questions on specific ones, or you'll be able to ask them then. OK? All right. Can everyone see this up here? You might not be able to read the numbers from there, but you guys should have it on the sheet. If you didn't bring it, well, it's up here. OK? All right. Question number 1 here. The image shows the graph of y equals h of x. What that means is this line we're calling h of x. Why? Because there's values on here. We can plug in x and y values, and those values are on the line. Okay? When we say y equals h of x, that just means this line. Okay? All right. What is h of 3? What is the 3 replacing up here? It's replacing the x. So if I say what is h of 3, that means where on this graph does x equal 3? So we go over to 1, 2, 3, and we say, where's the graph? Where's the line? Well, it's right there. So what is h of 3? 9. Or you could say y equals 9. Okay. Okay, that was a little different than you might think. Okay. Now, next question is, for what values of x, so we're looking for an x value, does h of x equal 4? What did we say we replace h of x with? Y, because we said it equals that anyway. Y equals 4. So what value of x does y equal 4? Well, 1, 2, 3, 4. You go over here. Right there is where it is. And you got to look on that and go, where is it? Well, it's right between 0 and 1. I didn't draw it very well, but it's right between 0 and 1. So that means x equals 0.5. Not so hard. You just got to focus on what they're asking for. Okay? All right. And then the next question is, what's the y-intercept? This one should be a no-brainer. Y-intercept, we went over this for those of you who are here Thursday. I tried to beat it into you. Y-intercept means what? Where the line crosses the y-axis, right there. What is true about x values there? X is 0. So get this in your brain. The y-intercept is where x equals 0. That's important, and it will be very important in the next question. OK, so x equals 0. So the y-intercept in this case, it's at x equals 0. So you say y equals 3. That's the y-intercept. OK? All right, and then finally it says, well, let me write that y equals 3 is the y-intercept. OK. Then it says, put the function in y equals mx plus b format. What does the m stand for? Slope. What does the b stand for? Y-intercept. We already have the y-intercept. That's nice. We've already got most of this. We leave the y. We're going to have to figure out what the slope is. We leave the x, and we put in the y-intercept. All we need to do is find that m, and we have solved this. How do you find the slope? When you have the graph, so easy. Pick 2 points on that graph and figure out the rise and the run to get to between those 2 points. How about this point and this point? I don't really care which point you use. You pick any 2 points. How much up do I have to go? Rise. 1, 2, 3, 4. How much over do I have to go? 1, 2. What's the slope? 2. Y equals 2. Y equals 2x plus 3. There's your answer. See how easy that was? Very, very easy. And you can do it for any point. If I picked this point and the 3 there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 divided by 1, 2, 3, 4, 5. What's 10 divided by 5? It's always going to be 2 because the slope of that line is constant. Okay? And by the way, when you get this, okay, that line, that is the definition of this line. So if we plug in if we plug in, let's see, -5 for x. -5 times 2 is 10 plus 3. -7. Look at that. It's at -7. OK? Magic. All right. OK. While we're on this, how do I find the y-intercept from this? 0 for x. So what's the y-intercept? 3. How do I find the x-intercept? Plug in 0 for y. 0 equals 2x plus 3. Well, now we have to do a little bit of algebra to get x by itself. What do I need to do? How about subtract 3 from both sides? I get -3 equals 2x. And then what? Divide both sides by 2. and I get x equals -3/2 or -1.5. Well, let's see. Where does it cross the y-axis? I mean the x-axis. At -1.5. Ta-da! Not so bad. Okay. All right. Let's go on to question 2. Any other questions on question 1? Okay. Question 2. This is a no-brainer. Everybody should get this right. Is that a function, A?
Yes.
How do you know? Because it passes the vertical line test. If you draw vertical lines through it, the line never hits the graph more than once. How about B?
No.
Not a function, because you can hit it twice. How about C? It is a function, because you... OK. All right. Hey, guess what? This question, how long did we spend on this question the other day, guys? Like 20 minutes? All right. Find the slope, y-intercept, and slope, x-intercept, and y-intercept. So we need to find the slope, we need to find the x-intercept, and we need to find the y-intercept. OK. The easiest thing I think to do is to find the intercepts first. How do you find the x-intercept? Plug in 0 for y. So this is going to be 3x minus 0 equals 15. And what do? Divide by 3. X equals 5. OK, I'm done. That's the x-intercept. And if I drew it in points, it would be what? 5, 0. OK, that's the x-intercept. The y-intercept. If I want to find the y-intercept, what do? Plug in 0 for x. 0 minus 5y equals 15. Divide by -5. Y equals -3. If it was in a point form, it would be 0, -3. Now, to find the slope, there's 2 ways of doing this. You could either turn this into the form y equals mx plus b. And this is what we spent some time doing on Thursday night. I think an easier way is the following. If you have this point and you have this point, we know how to find the slope. And it's really easy. x1, y1, x2, y2. y2 minus y1 divided by x2 minus x1. y2, -3, minus y1, 0. Oh, that's nice. x2, 0. Minus minus x1, 5. Oh, that's nice. -3 minus 0 is -3. 0 minus 5 is -5. The slope is 3/5. So that's probably an easier way to do it than to redo the equation. Well, if you're good at the algebra to resolve it, it's easy. If you want to just solve this, well, let's see. The first thing you could do is move the 3x to the other side. So you get -5y equals 15 minus 3x. And then divide both sides by 5. So you get -5, I guess. So you get y equals 15 divided by -5 is -3. -3 divided by -5 is 3/5 x. And there's your slope, right on the x value there.
Is there a way to check that?
Is there a way to check that? Good question. You could graph it. Yeah, you could graph it. Yeah, but and it wouldn't take too long to do. OK. Any questions on that one? Learn that and then. OK, that's 8 points worth? 10 points. 10 points. OK. All right. Well, guess what? If we did the slope properly on the last time, this is another no-brainer. y2 minus y1 over x2 minus x1 is your slope. Good. x1, y1, x2, y2. I did it wrong on the practice quiz. I did it wrong, just so you know. y2 minus y1, -1 minus 3 divided by x2 minus x1. 9 minus 2, -4/7. And that's 8 points, just like that. All right. Okay. All right. The next question, there's a couple things about this question. First of all, you have to use your calculator. So you have to know how to use your calculator for this one. Second of all, OK, you have to figure out what it means when it says X years after 2002. It's not hard. You just have to realize that the word problem like this, you have to plug the right thing in. The function f of x equals, or y equals 8 plus 38 L out of x, models the percentage of cell phones with cameras after 2002. Use the model to determine the percentage of new cell phones with cameras in 2007. So if we want x in 2007, what do we have to do? 2007 minus 2002, because it says after 2002, 5 years. X equals 5. And then you just plug 5 right into here. 8 plus 38 natural log of 5. When you do that on your calculator, what do you get? There's an ln button, which is nice. 8 plus 38 times natural log of 5. 69.2. 69.2%. Let's see how well this model works for now. What would we put for x for now? 2013 minus 2002, or 11. Plug in this. 8 plus 38 natural log of 11. 99.1.
And I know the 0.9% of the person who doesn't have it.
Well, and that's the point. The point is that by now, this actually means most people have phone. When you can barely even buy a phone these days without a camera in it, right? Yeah. Unless you're in Djibouti? Yeah. Maybe. I don't know. Natural log of 11. Yeah. Yeah. In Djibouti you can, sure, but no. Anyway, unlikely. OK, so you need to know a couple things to be able to do that one. Questions on that one? OK. All right.
What's like the tip-off that you'd be using that button?
The ln. The fact that it says ln in the formula.
You weren't here last class, so don't worry about it.
Yeah, you weren't here last class. Maybe you didn't do ln stuff.
Thanks, everybody.
All right. Yeah. Well, watch the videos. On the videos. OK. This problem, this one is a fairly straightforward problem to solve. OK, you can do either substitution or elimination. I happen to like elimination for this one. I think it's easier. But with elimination, you have to make these formulas such that when you add them together, one of the variables drops out. You can. Yep, you can do we'll do the substitution in a minute. Okay. First, let's do the elimination. Elimination method. What do you have to multiply the first one to get one of these ones to drop out? 7. That's easy. If we multiply the top by 7, we get 21x minus 7y equals 21. If I add these two now,
why are you doing minus? Why are you doing minus? It should be
plus. How's that? And that one's plus. Right. OK. If I add these two, I get 25x equals 125. And then that's one simple algebra step by dividing both sides by 25, x equals 5. We're almost done. You have x, but you also need y. So plug that back into any one of those. The first one's easy. 3 times 5 plus y equals 3. 15 plus y equals 3. Subtract 15 from both sides, and you get y equals -12. To check this, you should plug this x and y back into one of these. Now, somebody who will remain nameless emailed me the other day and said, I did check mine. I got a wrong answer for the homework, for one of the homework problems. And that person was absolutely right. OK? he or she did plug into one of the equations, but it wasn't true for the other equation. So you probably, if you really want to check, probably plug into both of them. Okay?
So the average didn't work.
You did it wrong. OK, now, any questions on the elimination method? You could also do this with substitution. For substitution, you solve for one of the variables up here, and then you plug into the other equation. Let's solve for y, because it's the easiest. All you have to do is subtract 3x from both sides of this. Y equals 3 minus 3x. Then you take the 3 minus 3x anywhere you see y in the other one, and you plug it in. 4x minus 7 times 3 minus 3x equals 104. Then you have to do a little algebra. 4x minus distribute, I like that, 21. Now what's this going to be? That times that. Positive 21x. 21x equals 104. And then you have 4x plus 21x is 25x minus 21 equals 104. So add 21 to both sides, and you get 25x equals 125. And it looks exactly like the previous problem. Okay. Either way, whichever way you want, as long as you do it right. Yeah. Yep. OK. All right. The next problem, I told everybody who came during the review session that this problem is harder than the one I will put on the quiz. This one you have to do, it's really 2 steps for this one. Okay? The way I would think of this one is I can't multiply easily to get rid of one of these variables straight off the bat. But if you notice the first one, what can you do to all those to simplify it? Divide them all by 3. 4x minus 5y equals 6. Now, if I had started with this, 4x minus 5y equals 6, then can you see how you can easily multiply this by, say, negative 7 to get this? So let's do that. Negative 7. Negative 7 times 4 is negative 28x. Negative 7 times 4x. Negative 7 times negative 5y is positive 35y. Negative 7 times 6 is negative 42. Now I'm left with these 2 equations that I've got to add together. 28x minus 28x is 0. Negative 35y plus 35y is 0. Oh, I think there's a problem. Houston, we have a problem. 40 minus 42? 0 equals negative 2. There is no solution. OK? And what did we say these look like on graphs together? If I graph that and graph that? They're parallel to each other, because there's no solution that fits both of those lines. Yeah. Oh, the graphing program, yeah. You know, if you have a Mac, it comes with it. It's called Grapher. Yeah, yeah, built in. Any questions on that one? I will not make it as hard as doing 2 steps for that, not on the quiz. Questions on that one? OK. All right. That one wasn't too bad. Once you knew how to do it, of course. All right. Uh-oh. Consider the quadratic function. OK. This is a parabola because it's a quadratic function. Does the parabola open upward or downward?
Positive.
How do you know it's upward?
X squared.
Because the exponent right there, which is a 1, is positive. So it's upwards. Okay. All right, find the vertex. Do we have a formula for that? X equals negative b over 2a. Which means negative b in this case, what's negative negative 2?
2. Positive 2.
2. What is 2 times 1?
2.
X equals 1. You're not done yet, though. Y is what you're looking for now. Well, just plug 1 into the formula. 1 squared minus 2 times 1 minus 15. 1 minus 2? Negative 1. Minus 15? negative 16. Y equals negative 16. That's a proper solution. X equals 1, y equals negative 16. Okay. All right, you ready? Find the x-intercepts. What do you do to find the x-intercept? What is it?
I forget the word, but
Well, you will have to do that, but you do have to factor. But the first thing you do is set y equal to 0. So you say, OK, this is y. F of x we just call y. 0 equals x squared minus 2x minus 15. Now, Sharifa said, uh-oh, we got to factor it, right? That's the word you're looking for? Yeah. So we do. We factor this. And we say 0 equals, OK, let's see, 15.
3 and 5.
Yeah, 3 and 5. And I know I'm going fast on this, but let's see. Which one's going to be negative? It's going to be negative 2 when you add them together. So it's got to be negative 5 and plus 3, because negative 5 plus 3 is negative 2. OK, you're not done yet, though. Set each one equal to 0. 0 equals x plus 3. Therefore, x equals negative 3. You can probably do that in your head. What plus 3 equals 0? Negative 3 plus 3 equals 0. And the other one is x minus 5 equals 0. X equals 5. Okay. If I'm going too fast on this stuff, it means you probably have to study a bit, which is fine. You got time to do it. Just be careful. X is negative 3, x is 5. That's fine for the x-intercepts. Y-intercept, what do you do to find a y-intercept? Plug in x equals 0. Well, this is easy. Y equals 0 squared minus 2 times 0 minus 15. Therefore, y equals negative 15. OK? Not so bad. Okay. Questions on this one?
What's the answer for B, please?
For B, the answer is x equals 1, y equals negative 16. It's the vertex. And we could, I didn't ask you to graph this, but you very easily could, right? You know it's going to be up and down. You know the vertex is negative 16 and 1, 1 and negative 16, right there. And you know that the x-intercepts are negative 3 and 5, 1, 2, 3, 1, 2, 3, 4, 5. And you know the y-intercept is negative 15. So there's your graph. Pretty easy, huh? Once you have all those points. All right. All right. And I think there's what? One more question? One more question. Nope, 2 more. This is calculator time. Log of 77. Just do it on your calculator. Log button, 77. And the reason you know to hit log is because it's written on there. All right. So whatever that is, I don't even remember. 1.9? Yeah. E to the 2.7, there's an E button, which actually does the caret for you, basically. You type E, or second ln, and it does the E, and then you do 2.7. You don't do the extra caret. You just do E, and then 2.7. 14 point whatever. This one you can just look at, equals 7. Because E and ln are inverses of each other. E raised to the ln of anything equals anything. But you should do it in your calculator to test anyway, and you'll get 7. Okay. All right. Now there's one more question. OK. I will ask you one like this. I will probably give you some hints on it. Right? But it's going to be somewhat similar, but it might not involve. It'll involve something similar, but you might have to think a little. I'm giving you that hint right now. Use your brain. When it says make a table of values, good, you make the table. That's the easy part. X and y. OK, this is y. So we're going to say y equals 3 raised to the x minus 2 minus 3. And it says use from 0 to 4. 0, 1, 2, 3, 4. I think I did this the other day. I did it, but I'll do it again. For 0, plug in 0 into this. 3 to the 0 minus 2. 3 to the negative 2. So you can do that on your calculator. It happens to be 1/9 minus 3. So it's going to be negative 2 point something. Negative 2.9 maybe? 2.9? Negative 2.9. OK, then you do plug in 1 for x. 3 to the 1 minus 2. 3 to the negative 1. 1/3 minus 3 happens to be negative 2.67. And you just have to use your calculator for this if you don't want to do it in that. This one's pretty easy. 3 to the 2 minus 2. 3 to the 0 is just, what's anything to the 0? 1. 1 minus 3? Negative 2.
Question.
Yeah.
For 3,
For
the one above it in the middle.
For this one?
We're not rounding to the nearest 10.
No. I mean, if you want to, you can. You could have put 2.7, negative 2.7. That's fine.
We're good with that?
You're good with that. I'm good with that. Yep. Just don't put negative 3. But put negative 2.7. Yeah, too much. OK, for 3, 3 raised to the 3 minus 2. 3 minus 2 is 1. 3 raised to the 1 is 3. 3 minus 3 is 0. And then finally, 3 to the 4 minus 2. 3 to the 2 is 9. 9 minus 3 is 6. And then it says graph it. And to graph it, you draw your little graph. You say x goes from 0 to 4. 1, 2, 3, 4. And y goes from negative 3, basically, negative 3, all the way up to 6. And you start plugging in 0, negative 2.9. It's almost right there. 1, negative 2.67, not very far up. 2, negative 2. Still not very far up. 3, 0. Oh, now we're getting somewhere. And 4, 6. Now we're really getting somewhere. And you graph it like that, and you're done. And you can tell it's an exponential function because it gets steep really fast. 5 would have been 3 raised to the 3, which is 27 minus 3. 5 would have been 24, right? Way up there. Just for 5. OK, it's exponential. Questions on that? Yeah, no? OK. Any other questions on the practice quiz? OK.